Welcome to my new calculus channel. I am John Gabriel, and in this new YouTube video I'm going to be discussing one of Georg Cantor's set theorems. It's actually more of an argument or a statement that he concluded from some very false or idiotic premises. And the question that I'm going to ask in this video is, are the real numbers countable? Well, first of all, let me give you the quick and dirty answer. The real numbers are not countable because they don't exist. And I have proved that in several videos of mine, which I shall show you in the comment section once I upload this video, or you may have already seen them. There's Academic Ignorance and Stupidity Part 2, there's Part 1, Part 2, and Part 3, and I believe Part 2 shows that there is no valid construction of the real numbers. Neither Dedekind nor Cauchy were able to construct the real numbers in a valid format. So in essence, the real numbers are not countable because they don't exist. But that's not the point that I'm going to argue in this video. I'm actually going to assume that they do exist, and I'm going to assume that the infinite decimal representation, or any radix representation, it doesn't matter, representation, I'm going to assume that the infinite decimal representation can be used to represent any real number, and I'm going to focus on one particular interval, the interval 0, 1, because using Cantor's nonsense of bijective cardinality, if we can show that any real interval has a bijection with this real interval, then what we have is we have a similar infinity, or an equipolant infinity. Okay, and what I'd like to demonstrate in this video is that if we assume, one, that any real number can be represented as an infinite decimal, then we can, first of all, we can represent all the real numbers. How? I'm going to explain to you now. All the real numbers in the interval 0, 1. Okay, and how do we do that? We use this tree. Basically, it's just a tree of permutations. We have our 0 point, this big black dot, and all the numbers in the interval 0, 1. Okay, and so we can represent all the real numbers in this interval using Gabriel's decimal tree. So we just basically start off here, and we traverse the trees as we go along like that, and that's the infinite decimal representation of each of those numbers. Or the finite, it doesn't matter, we can also have a finite decimal representation. For example, 0.10 or 0.05. Okay, I'll explain what these little red numbers mean in a moment. So we can represent all the real numbers in the tree. And thirdly, we can enumerate those real numbers. Now, this was something I was not able to do in my debate with this vile Jewish fool who owns the science blog. Now, I'm going to show you his blog in a second. I was not able to get there. This is his blog. He actually banned me before I could get to that part. So the blog is called Good Math, Bad Math. Of course, Chu Carroll is not a mathematician. He claims to be a computer scientist and has a PhD in computer science, which is quite remarkable because he knows very little about tree traversals. If you happen to read this particular discussion I had with him some years ago, you'll see that he's lacking in many respects. So at any rate, The only reason I engaged him is that he wrote a little blog on me, insulting me and saying that my null article, which I'm going to show you here now, that had extremely high ratings. In fact, it used to get, on null, it would get, I think, a few thousand hits a week. If you look at this particular week alone, on this page, I don't remember the date, but it was 3,582 page views just for that week, and the totals for all my nulls were 37,000. I was often awarded the top viewed author award and the top pick author award because I know what I'm talking about, and people understand what I say and what I reason and present logic to them which makes sense. So in this null here, which was written a long time ago, it had 135 ratings, and look at the article rating, 4 stars out of 5. Okay, it was also awarded top pick null award, and as you can see, many people do not accept this theory. Only the morons in mainstream mathematics academia are propagating this absolute rubbish. Okay, this is not even a proof, it's just an argument. It's called a diagonalization argument. Cantor was such a fool. He's what I would call the father of all mathematical cranks. Now, Cantor didn't start out that badly. For example, how did he get, do any of you know how he got his idea of a countable set? Well, I gave this quiz some months ago, or I think perhaps a year ago, on Quora. How did Cantor arrive at the idea of a countable set? And so the quiz says, test your knowledge by choosing only one correct answer. And so there are 4 choices, and it's pretty tricky because a lot of these here are misunderstood, and only one of them is the correct answer. The rest of them don't count. For example, ask yourself, why is it that any set that can be placed into a bijection with a set of natural numbers is countable, and yet the set of natural numbers is countable for which reason? Why do we say that the set of natural numbers is countable? And what is the reason for that? Okay, so it turns out that only one person was able to answer this correctly on Quora, and he was a master's math graduate from MIT, whose name is Anders Kesor. He chose the correct answer. In fact, the correct answer is that n is countable because each element has a unique name. That is what it means to be countable. Okay, the little guide that is given in real analysis courses to students who are learning about this crap theory is that if they can place a particular set in a bijection with n, then it is countable. That's just to make it easy for them. The real reason is that n has elements which all have distinct or unique names. Okay, how do we know that? Well, every element of the natural numbers has a unique identifier in any radix system. So you could say, well, okay, if you go to base 10, let's just go back here. So in base 10, we have 0, 1, 2, etc., 1, 2, 3. So we have a template here: units, tens, 1 over 10, 10, 10 squared, 10 cubed, 1 over 10 squared. So we can represent, using just this section here, every natural number uniquely. Every natural number has a name, right? Okay, a unique name. And you can think about that a little bit and see why it is true. So this is why the set of natural numbers is countable, because it has elements that are clearly distinguishable from each other. Okay, so Cantor realized that, and he didn't start off too badly. You know, I mean, that's a good realization to make. It's just where he ended up was quite absurd. But I'm not going to go there right now. So at any rate, N is countable because each element has a unique name. And the next comment in this link, which up here, which I will provide in the comment section so that you can read it, explains each one of those choices, okay? There's a lot of confusion among set theorists and topologists regarding what it means exactly for a set to be countable. And I'll go ahead and I'll explain here why those choices that are not wrong are wrong, and show you why option 3 is the correct choice, okay? So let me go back to this diagram over here. So anyway, in my debate with Mark Chu Carroll, I began by saying that, well, first of all, he has to agree that I can represent every real number in this interval using my decimal tree. He didn't seem to have a problem with that, because I could do that, finite or infinite representation. Later on, he did stumble on this part here. I'll explain that as I go along. And he also didn't have a problem with representing them, obviously, so the only problem that he had was with the enumeration. And I'll explain how you can enumerate this, because I was banned before I could do it on his website. Just look at how it started out with Chu Carroll. He wasn't interested in debate. First of all, this was my first response to him. I tried to say, let's drop the insults and start again. And so he didn't bother, reading this and immediately answering it or cooperating with me. No. Rather, he began to make statements that were incendiary. For example, he said something about, you can already see the flavor of what's coming. Johnny is rather a control freak who is fond of dictating terms to people. All he had to do there was simply answer the questions. He eventually did give a yes answer to all of them except 4, and I'll explain why he didn't do that. Okay. So if we go down along, let's just quickly look at this argument here. You can read it for yourself. I'll also put a link to this section here so you can read it. But his reason is that he believed that while you could represent all the numbers, you could not enumerate them. So he says eventually, but fine, after all that vitriol and whatnot, he comes back and he says, but fine, I'll give you answers. Yes, I'll agree that all the real numbers are representable using infinite decimal notation. 2, I'll also agree that taken to infinity, your tree contains all real numbers between 0 and 1. 3, yes, I'll agree that all finitely represented numbers can be enumerated from your tree using a breadth first traversal. And 4, no, I do not agree that you can do a left to right traversal of the infinitely long representations. Okay, and then he seems to have a problem with 1/3. And I'll show you now that that's not even really a problem. And he's not even interested in debating, so he says this is something that is going to come up again and again. And so he's really not interested in debate. He's just interested in ad hominem and making it interesting to attract readers. So I ignored him and I said, very good. Now let's address your issue with question 4 so that we can move on. And so I said to him, well, if you can't do this, then I do not see how you agreed with 2. Let me clarify it with you. At this time, we do not care about ordered traversals, only that the traversals are possible. Cantor's original argument says nothing about the order of numbers, only that these have to be placed into a one-to-one correspondence with a subset or the set of natural numbers. Okay? So I was wanting to get to the enumeration. All I wanted him to do was to allow me to get to the enumeration, but I couldn't get to it. And now I'm not going to waste time on his ridiculous blog, because most of it is meaningless nonsense. And if you look at all the comments by his patrons, they're a bunch of idiots who don't know what they're talking about, who were only there to write ad hominem comments and insult and throw around all sorts of nonsense which was not even related to the topic. So at any rate, let's go back here now and see where this fool, Mark Chu Carroll, failed. Okay. All right. So now let me just get rid of this here. So, oops, clear up some space. Okay. So Carroll did not have a problem with representation. All right. Representation of all the numbers in the interval 0, 1. He had no problem with that. Okay. Now, how do we, let me explain what these little red numbers mean here, because that's crucial to my argument that you can create, that if the real numbers in the interval 0, 1 are represented by decimals, you can create a bijection. Okay, what is a bijection? It is a one-to-one correspondence between the elements of two sets. So now, I'm going to let all the real numbers in this interval correspond to unique sequences. So for example, 0 is just 0, 1 is 1, 2, 3, 4, 5, up to 9. Once I get to 9 here, this is the first up-down level. In the next up-down level, I'm going to assign this number here, 0, 0, 10. And if I had a 1 there, it would be 11, 12. When I get to 5, it's 15. And I think you get the idea, right? And so when I get down to the end here, I would have had 100 as a sequence. So the next one is obviously going to be 101. So now the idea here is to map these red little sequence numbers with the decimal representations. Okay, so we need to map those uniquely. All right. So now let's see how we do that. Well, supposing you gave me the number 0.05 and you asked me to find the sequence number. Well, then I come over here and I traverse a tree until I get to 0.5 and I see, it's 15, so 0.5 gives me 15. Yes? Now suppose you gave me 15 and you asked me to find the number. Okay, then I'd do top-down traversals until I find 15, and they'll say, that's 5, and then I just trace it back to the origin, right? Trace it back to the origin. And that would give me 0.05. Yes? Okay? So it's very easy for me to create a bijection, but so far you might say, well, okay, well, these are finite numbers. That's true. Now, how do we do it with infinite numbers? Well, let's take the case of pi. Yes. So the case of pi, which is 3.14159, etc. Theoretically, you'd have to give me all the digits if you wanted the sequence number. Do you agree with that? But since you cannot give me all the infinitely many digits, because it's impossible and it just can't be done in any fashion, you might say, okay, give me 3.141 ... Alright? Or 3.14. Let's just make it 3.14 to just simplify the argument. Hang on a second. 3.14. So we've got 3.14 here. 0.314. I'm going to take the fractional part of pi, not pi, the fractional part. So 314, right? Okay, so you say, okay, give me the sequence number for 3.14 ellipsis. Why can't I do that? Of course I can do that. That's what mathematicians do when they write pi. They put an ellipsis after any of the sequence of numbers. So I can represent pi that way here, can't I? So all I do is I come along and I say 314. So the sequence number there will be 414, and I'll put ... meaning that it's one of the possible sequence numbers, given that I do not have all the digits that represent the fractional part of pi in the real numbers. Okay, So I can do it also with infinite values. And the last problem that the idiot Mark Chu Carroll had was with 1/3. All right. So he says, well, the infinite value of 1, he told me that 0.333 is not in the tree. Well, of course it is. Okay, here's 0.333. All I have to do is find the sequence number and add an ellipsis. If he gives me 3333, then I'll go to the next level, find that sequence number, and add that. Okay, so it's very possible to have a bijection between all the real numbers in this interval and the sequence numbers here. Now remember, if it's infinite, you need all the infinitely many digits. But of course, non-terminating or infinite representation is rot. Okay, Simon Steven began this rot. You cannot say that is equal to 1/3, and there is a YouTube video on that too, where I explain that this ellipsis here doesn't mean it's infinite. In fact, there is no such thing as an infinite representation, as most morons in mainstream media, mainstream academia think. There is no non-terminating representation. So at any rate, you can create a bijection. A bijection is just simply an algorithm in this case that I'm demonstrating here. Okay, it's an algorithm. And that's really what a function is. If you, for example, consider Cantor's pairing function, which supposedly proves that the rational numbers are in bijection with the natural numbers, it's not actually, strictly speaking, true, because in his original German definition, Cantor stated that all the rational numbers can be placed into bijection. That's not true. Not all of them can. Yes, you can have a function, but as I explained in another video on Cantor's bijective cardinality, it's not true that you can take one line like that and another line like that and say that they have the same amount of points. You can't count points. So Cantor was really the originator of a lot of ridiculous, absurd, and false theory. Okay, he really did a tremendous amount of damage to the progress of mathematics. And of course, David Hilbert came along later on, a complete moron, and made things far worse. So what we have here now is the answer to this question: are the real numbers uncountable? Are the real numbers countable? Well, they are not countable because they don't exist. But if we make the same assumptions as Cantor did, then they are countable, because we can create a bijection using the scheme I showed here. And it's possible to enumerate. It's possible also to enumerate, as I've shown with these red sequence numbers, all the numbers in the interval 0, 1. And hence, if we can enumerate them, in other words, we can give them unique identifiers, then we have in effect shown that the set is countable, and it can be put into a one-to-one correspondence with the natural numbers. You might tell me, okay, well, you haven't given me the exact sequence number of pi. Well, guess what? You haven't given me all the digits of pi. And you can say, well, you haven't given me the exact sequence number of 0.333. Well, you haven't given me all the 333 digits. Otherwise, I'd be able to give you the sequence numbers. So this is part of the reason why infinite decimal representation is a lot of junk. Okay? You cannot have infinite decimal representation. So this evil, filthy Jew spent a lot of time in his blog. As you can see, it's pretty long, denigrating, continuing here. Watch this here, where this particular comment here, where he says, traversal of a node doesn't mean saying it's down there somewhere. It means visiting the node. You can't touch the parent of a node in a tree and say, I know the child is down there somewhere, so I have traversed it. Watch my response. As I just explained to you, I have a systematic way of visiting each node once. As for saying I can't touch the parent node in a tree and say the child is down there somewhere, oh yes, I can. This is part of the beauty in computer science algorithms. They are predictable. Tree structures are designed the way we want them to be. I wrote complicated balanced tree algorithms in assembly x86 way back in 1980. Trust me, if I could not say the child is down there somewhere, I would have had major issues. Do you know anything about algorithms and optimizations? Probably not much. Okay, so at that particular time, Chu Carroll worked at Google. I think he now works at Twitter. So Google got rid of him, I think, for some unknown reason. I'm not sure. But I suppose they made the right decision because he wasn't very smart. And he was working on a cloud API. He even wrote a book on it. A load of junk, actually. I read a little bit out of it. I wouldn't pay a cent for it. And so Mark Chu Carroll here is just a privileged white Jew who decided he was going to denigrate my name and try to make me look like a crank. In fact, the real crank is this bastard here. And I can't express the amount of hatred I have for this individual. If a bus had to hit him, it would make me really glad. But of course I'd want him to die slowly and horribly, not a quick death, because he doesn't deserve that. Here's another thing about this individual. When he was living in White Plains, New York, and still at school, he was so unpopular with his schoolmates that they broke his fingers. And so he apparently trained his son to do karate or kung fu. And by the way, all this stuff is on the web. That's how I know it. So I'm not revealing any information here that's private or that hasn't already been placed out on the web. Even his photograph here is on the web. There are several other photographs of him. So I have nothing but the highest contempt for this bastard. And I hope that you can see now from what I've done here in this particular scheme that you can create a bijection between the numbers in this interval, if they're representable as infinite decimal representations, and the set of natural numbers. And I think you may have learned also one other important fact. Okay, the other important fact is this, that a set is countable if its members have distinct names. So can you see that if you have a tree like this, if they are infinitely long, you don't even know the names. How can you count objects for which you have no unique tag? You cannot. So if you traverse this tree infinitely from left to right, you can't. It's impossible to do an infinite traversal. That's why you can say, all right, well, 0.3. Actually, I did this wrong here. I made a little mistake here. This tree here should have been attached to 1. But I think you get the idea. I just saw that now. Okay, well, that's just too bad. But if you have 3. The fractional part, I made a mistake earlier. Fractional part is 14159. So I really should have put this part of the tree up here and shown you how it works. But I think you get the general idea. If you just go over this by yourself and study it. I hate Cantor and I hate going over this. I've done it many times. I do not want to waste any more time on it. As I've proved here, it is possible to create a bijection. Cantor was a fool. Modern set theorists and topologists are fools. Don't waste your time on Cantor's theory or set theory or topology. They are the most useless fields of study. Okay, and so I hope that you will have learned something in this YouTube video. This is the New Calculus channel, and I'm John Gabriel. Till next time.